Okay, so question 9. So we're beginning with moving into electrostatics. This is the 115 exam 2 review. So we've got 2-point charges of equal magnitude are 7.5 centimeters apart. At the midpoint of the line connecting them, their combined electric field has a magnitude of 45 newtons per coulomb. Find the magnitude of the charges. Okay, so again, let's start with the picture. And I'll draw the charge here. And then it's separated, I'm doing my rotor, 7.5 centimeters. From another charge over here. And then we're told at this particular point, so it'll be 3.75 centimeters. Here's a combined, their field has a magnitude of 45 newtons per coulomb. Now, you could be asking yourself the question, what direction is that point in? Are these two positive charges, two negative charges, opposite charges? So it's a good question maybe to start with. So if these are both positively charged of equal magnitude, the electric field at the midpoint will be 0, because one charge would have a field to the right, the other charge will have a field to the left, and since they're the same magnitude and the same and the midpoint between them, the field will be 0. That would also be true for two negative charges. So they have to be a different sign charge in order for the field between them to be non-zero at the midpoint. So and this is arbitrary. I'll make this one a plus, I'll make this one a minus. So the electric field due to the, maybe I should draw this, maybe I'll need this in red. So it will have a field that points away at this point. So I'll make this E of the plus, and then this one, leave this one in purple here. This will be E of the minus, and they will, because they're equal magnitude charges and their equidistant from this point, they'll have the exact same magnitude of E field. So I can write that the E net is equal to E plus plus E minus, so they're both pointing in the same direction. And this is going to be given as Q plus, which is just Q, over the R plus distance to be squared, plus the K of the Q minus over the R minus squared, but these are both the same. So R plus is equal to R minus, which is equal to the distance between the two charges. If I call the distance between the two charges R, this is R, then of course the midpoint has to be, so R plus is R over 2, same as that as R minus is R over 2. Hopefully that's not too confusing, too many R's. Okay. So here I have got basically 2 KQs over R over 2. So this in a sense becomes 2 KQ, where this is Q represents the magnitude, divided by R over 2. And that just leaves me with 4 KQ. Oh, sorry, it does not. I forgot the square. So that will be equivalent to 2 KQ over R squared over 4, which leaves me with 8 KQ over R squared. So we know all of this is equal to 45 newtons per coulomb, and I'm trying to solve for Q. Oh, and yeah, correct. Okay, so 8 KQ over R squared is equal to 45 newtons per coulomb. So my Q will be equal to 45 newtons per coulomb times R squared, all divided by 8 times K. So this would be equal to 45 newtons per coulomb. My distance is R is 7.5 centimeters, so that's 0.075 meters all to the squared, all divided by 8 times 9 by 10 to the 9 newtons per meter squared per coulomb squared. And this should leave red. 3.5 by 10 to the minus 12 coulombs. So let's try to see. Hopefully I wasn't too confusing with the ors, and maybe I could have labeled this into different letters, but the midpoint line will represent or over 2 for each of these. They have to be oppositely charged in order to get a non-zero field at the midpoint. So then in an algebraic sum of 2 kq's over the half the or distance, which is or over 2, do some of my algebra, and bring the 4 up to the top. 4 times 2 is 8, set that equal to the net field, and then solve for the value of q.